All right. Thanks, Bruce. Thank you. All right. So I got y'all trapped here for like almost an hour. So what we're going to do over this time is, first off, I'm going to talk about the very origin of the rocks in our area. So we're going to do basically some geology. So we'll do some real basic geology. And then we're going to go into a little bit of history of study of the aquifer. We're going to get into the study of the aquifer, a study of hydrogeology, which is about the groundwater flow. And some of the mysteries we're going to try to answer in the next hour, a lot of mysteries to look at, and some of them are like, where does the water come from that feeds Barton Springs? And some other questions like, what can you all do to help sustain the aquifer? And some of the new science about the aquifer that's been going on. Some of the new science is actually really old science, and we'll talk about that too. Okay, it's been known for a while. But we've had changes in the way we look at things, so I'll tell you how I look at it today, and it's all true. It's all true, in my opinion, anyway.
It's all true.
Yeah. Can you all hear me back there, or do I have to be louder? Okay. Let's start off with the origin of the rocks in the Austin area. So if you look back, the Cretaceous era, the Cretaceous system was from 140 to 65 million years ago, so a long time ago. At that time, I say it's about 100 million years when the rocks were laid in the Austin area, okay? Austin looked a whole lot different 100 million years ago. It looked like this. It was an ocean. I also have my partner here, by the way, is Tara. And you want to help me with Tara?
Yeah.
Okay, awesome. So this is Austin 100 million years ago. A shallow sea covering inland through most of Texas, going all the way up to Wyoming through the continental United States. So a lot different than it is today. Okay, you can imagine Bahamas all the way up in Austin area. Okay, so what was it like? You had shallow waters, and sometimes you had deeper waters. You had large swimming reptiles, not the kind of place you want to go swimming like Barton Springs today. We're talking huge, these are plesiosaurs and mosasaurs. Ichthyosaurs, really large swimming reptiles that were, from here to that tree there. These are big. And if y'all ever want to learn more about this aspect of the Austin history, let me tell you this, as you go across the street to Botanical Gardens, and they have the Hartman Prehistoric Garden, and you can see footprints of some of the smaller dinosaurs that were ostrich-sized. I say smaller, but they were ostrich-sized. The Omnithomimus. They have a replica of it there across the street of the Botanical Gardens. And if you go to University of Texas, to the Texas Memorial Museum, there they have exhibits. They have some of the bones of the mosasaur that they pulled from Onion Creek. They have the plesiosaur that they pulled from Shoal Creek. They have an ichthyosaur, which is like a large meat-eating dolphin, right, as a reptile, that they got from Marbridge there in Bear Creek. So you had all of these things in the rocks that were from 100 million years old, that were swimming in the ocean at the time. Now, most of the time, when the Edwards Aquifer was laid down, the Edwards was a certain group of rocks that was laid down about 100 million years ago. It's about 400 thick package of rock, right? And you have all kind of bizarre fossils, like this guy is the most common one. It looks like a dip cone from Dairy Queen, about the same size as one, and it kind of whirls around. And it's a mollusk. This is a resin replica because they don't show very well. But if you're a good scout and you walk around, and you look at the rocks, you'll see here's a Tucassia here, the same fossil. This is what it looks like in the rock, like this. So as you're walking around and you're observing, you can see the fossils in the rock that for 100 million years old that are signs that we were once in an ocean environment. Some of the other fossils we have are like these scallop shells. These are called pectins. We had corals, and then if you go walk the Wildflower Center, a lot of times you'll see rocks like these that are really kind of heavy and dense, and they have these little branching sticks in them that are actually coral from 100 million years ago. So this is what Austin was like 100 million years ago. There's ample evidence around it. So one of the mysteries then is why were the oceans so high 100 million years ago? I wonder if any one of y'all have an answer to that. Maybe like Noah's flood or something, right? Could be that. And anyone have an idea why were the ocean levels that high?
Lots of carbon.
Yeah, what would you say?
It was high.
Yep. Lots of carbon, ice cap. And that's exactly right. Is you don't have any more water now than you did 100 million years ago. But they were different phases, different forms, right? So you have ice, you have water and ice, and you have water and humidity in the air, which I feel today. You have water in the ocean. Okay, so 100 million years ago, you had these guys that were like simulating industry plants' emissions these days. There were a lot of volcanic activity 100 million years ago. They're venting off fumes, a lot of activity around the world 100 million years ago. In fact, in the Austin area, we have at least two volcanoes. We have more than that, actually. But one of them you can go see it under St. Edwards University is a volcano. It was built on an old volcano. And if you go across the street to Blunt Creek Preserve, you can see some of the volcanic ash from that volcano. If you go near the airport, south 183 from the airport, there's a hilltop with a water tank on it. And you'll see a sign in front of it on the highway, and it's called Pilot's Knob. Pilot's Knob because the pioneers used to use that as a landmark to find Austin. But that's an old volcano. And what some of the volcanic rock looks like is this is a piece of basalt, which is a volcanic rock from the Austin area. Piece of basalt, probably from Pilot Knob. Some of the other volcanic rocks you have, they're not actually volcanic, but these are hot molten rocks from the Enchanted Rock area. This is called granite from like the Enchanted Rock area. Now the difference between this and this is this cooled really quickly at the surface. It's like a volcano that came to the surface and cooled, whereas this cooled really slowly below the surface. So the crystals are really big. You can see crystals like quartz, the little orange crystals that are plagioclase that break down into clays, and some flat minerals in here too. So you can see the minerals are really big because they cool below the surface of the earth really slowly. And that's how you can tell these two kind of, they're not, this is volcanic and this is an intrusive rock that cooled below the surface. So a little history of the Austin area, that's why water levels had risen, because you are emitting these fumes. They trap the heat in from the volcanic fumes. And it happened so slowly over periods of time that a lot of organisms in the 100 million years ago could evolve, because the change occurred fairly slowly at that time. Nowadays, things are happening pretty fast. Water levels are coming up pretty rapidly. So what happened is the hot environment from 100 million years ago caused the ice caps to melt. There was no ice on the North Pole, South Pole 100 million years ago. So it all had melted in the ocean. And what does that tell you looking at the rocks? It's like, what could happen today if you completely melted the ice caps, right? We got marketable oceanfront property here in Austin. Not just the 3-foot rise we talk about nowadays that, we can only imagine a 3-foot rise. Well, it can get a lot higher. I mean, historically, it has happened, right? So just keep that in mind also. But this was life 100 million years ago. Huge ammonite shells. This is the kind of fossil you might find actually in Barton Springs on the east side of the pool. Okay, the ammonites are found in that formation called the Georgetown. And the environment's really different in the Cretaceous. It wasn't all the same. The rocks deposited on the shallow end of Barton Springs were formed under a heavy wave action environment. A lot of waves, and they had these little floating creatures called foraminifera that would float in the rock, and it made it really hard. So if you've ever been upstream to not Sculptor Falls, but Campbell's Hole, and you see that moonscape, it's the same rock. It's packed full of those little floating organisms that make it really resistant to erosion and dissolution. So you have these moonscapes forming. A little bit like in the shallow end of the pool on the floor. Now the walls of the pool have these very thin fissile rocks that are thin bedded, just like the stuff you see coming down the hill when you're driving to Barton Springs, these thin beds. Thin beds are unusual in the Edwards. What happened there is you had a really quiet environment, so you had mud forming in the bottom, just being laid down in the bottom. Now the stuff down below, 40 feet below Barton Springs pool, that's the most cavernous material. It's called the Kirchberg Formation. After the Fredericksburg area, it means Cherry Mountain is what it was. And in the Kirchberg and the Fredericksburg area, you can actually mine salt out of the rocks there. Because the environment there was like a bowl where you had lagoons and you had tidal environments. So basically a bowl where you're evaporating the water, and so you're getting all the salt just precipitating out of the water, and you have this really soft material that can form things like caves all across the Austin area. So this Kirchberg member is the most cavernous layer in the Austin area because of all that soft material in it. So you can put that poster down. Thank you all very much. What's on the back here? I'm not ready for that yet there. So that was 100 million years ago when we had the oceans here. Where do we put no, I was looking for this bag that I had here. Hey, Laurie.
Hi, what do you need?
Ah, I lost it. Okay. I had a karst exhibit. You able to find that? It's in a brown bag. I must have lost it somewhere. I hope not. It's my wife's. So that was 100 million years ago. We're covered with an ocean environment. No, it's a big old brown bag. It has a... Uh-oh. Okay. If you can find it there, that'd be awesome. So that was 100 million years ago. That's the environment that Austin was formed in. And you had all of these original Austinites. These are founding Austinites right here, right? And I brought these here because if we had any kids over here, and adults too, you know, this is a great way to experience life in the Cretaceous, is playing with these models. And I brought a little scene here that I made. It's not one of my best Cretaceous scenes, but this was what Austinites looked like 100 million years ago. And we say we like Austin weird, right? So they were definitely weird. You had these guys flying over the skies, and they found remains of these in Big Bend National Park. Now, much later, you know, we're talking just thousands of years ago, we had a whole new population of Austinites, and these are these guys. These are these mammals now, right? They're not the reptiles we're talking about before. These are mammals. Things like the woolly mammoth they found in the downtown Austin area. These were coexisting with people at the time. During the last ice age, these are giant sloths that could be as tall as this. They could eat the leaves off the tree. These vegetarians. Now this guy's a glyptodon. It's the size of a Volkswagen. Yeah, with a spiked tail. It's a mammal. Isn't this bizarre? Now in cave exploring, sometimes we'll find the hexagonal plates from their shell. They're this big in the caves. Okay, these are awesome little creatures that aren't here anymore, called glyptodons. And this guy, by the way, can y'all tell what this is? You want to tell? What does this look like? Dinosaur, exactly right. So this is a track from the South San Gabriel River just upstream of 183. There's a sequence of footprints of this guy, which is an Anthrocampsosaurus, which is about the size of a T-Rex. He's a really large meat-eating dinosaur that was here at the time. And so you had these guys around on the shore, walking on the shore, but a lot of ocean, shallow ocean in between with marine shells. That's just what Austin was like 100 million years ago. So one of the mysteries, and to look at, if you look in the Austin area now, no ocean, right? Because why did the oceans go down? Who knows? Why don't we have an ocean here anymore?
Uplift?
Nope. Wasn't that much uplift. There was some, not a lot. Actually, some of the Gulf Coast subsided down. Yeah, Ice Age, right? Got cooler. Cretaceous was one of the hottest periods in record, and so thereafter it got cooler a lot. It was a lot cooler thereafter. So the ice forming in the poles caused the ocean levels to drop down. Exactly right. And so now you have rain falling on the landscape and starting to dissolve away the rock. And so this is one of the mysteries about the Austin area. You have a 5-mile wide stretch where you got lots of caves. Where you go to Bass Strip area, no caves, all the way to Houston, right? Not really much in the way of caves. Going to the west of Austin, not much caves either. You got Enchanted Rock, a cave there, and some caves in the between here and there, Jacob's Well. I can't deny it. A lot of caves in the lower Glen Rose formation, but not that many. There's a 5-mile stretch where you have lots of caves, and the secret of that is the rocks and minerals. So we'll go a little bit in geology now. Now, understanding rocks and minerals, it's just you can visualize a house, right? A house that's made of bricks. Now you look at a distance and you just see a house. You don't see that as a pile of bricks. But rocks are kind of the same way. When you look at this rock here, you don't see that there's a ton of little minerals that are making up this rock. So you can imagine this is like a house. This house is called Limestone Rock, and it's made of small minerals, which are like these guys. This is a mineral called calcite. Looks kind of like a squash cube, doesn't it? I'll pass this around, you can look at it. And I didn't cut this out of rock. This is the way it forms. If you were to hit this with a hammer, and don't do it please, but if you were to do it, and you look at it carefully, you can see there's a ton of more cubes that are inside here. It breaks into small cubes just like this. I'll pass this around to look at it. Pass one over here and one over here. So this is calcite. And this is real key because, you want to take a look at it? Because what's special about calcite mineral is it dissolves away fairly easily. Dissolves away fairly easily. You put enough rock through it and it dissolves away fairly easily. Here's an example of a limestone rock where you have water dissolving through it, making holes in the rock. And the reason why you have this texture, by the way, called honeycomb rock, generally because you had fossils in here that were things like this fossil, or some long tubular fossils, or sometimes they were shrimp burrows. They got preferentially dissolved away. They were a little easier to dissolve them away than the rock around it, making this honeycomb texture that you see both in the Austin area. Here's another example.
Calcite, then?
Pardon?
So they were calcite, and that's why they dissolved.
Exactly right.
preferentially?
Exactly right. Very characteristic of the Austin area. And by the way, if y'all have questions as I'm talking along, feel free to raise your hand. And
I've always wondered, when did Barton Springs, the spring, actually form?
yeah, that's a really good mystery. How old are them? That's a really good question. We'll look at that. We'll look at that some more. How about how Barton Creek formed? It's tied into that. We'll talk about that too. That's a really good question. Let me cover a couple more minerals, though, by the way. And here's calcite looking like a massive rock. Usually you don't see the crystals this big, but they're really small crystals inside rock like this. Now let me show you some other common minerals in the Austin area. And one of them, I showed you this piece of granite from the Enchanted Rock area. You don't have this in Austin. In Austin itself, if you look at the creeks like Barton Creek, you don't have granite in the rocks. But you know what? I live out upstream on Lake Austin over there at like up Bee Caves Road. And in my backyard, sometimes I'll see really round rocks of minerals. This is quartz mineral. This is quartz. Quartz is a lot of times a clear crystal that forms little prisms. And this is quartz. Here's another example of it. It's all nice and rounded. So it's kind of a mystery where this comes from, because it doesn't come from limestone rock, that's calcite. So where does this come from? And the answer to that is that it came out of rocks like this in granite along the Colorado River. And it came down. The quartz out of this rock is the thing that's going to be the most resistant. So you might get chunks of quartz left over and everything else turns to clay. Okay? So what you'll see are these, when this goes down 10 miles, 20 miles down the Colorado River, this turns into this. You do not see these naturally in Barton Creek, Onion Creek, any of the creeks in our area, but you'll find it along the Colorado River. Okay? I'll pass this around. These are quartz crystals that are rounded from traveling through the rivers, the Colorado River. And by the way, you're welcome, by the way, if you want to, you can welcome to play with the dinosaurs in case you want to do that, because I love doing that too sometimes. So another quartz crystal is this guy, and this is more common on the Edwards. This is called Chert or Flint. It's the same crystal material that's forming quartz. And quartz, by the way, is the same stuff that's in window glass. Windows don't dissolve real easily, thank God, or else we'd be in a lot of trouble, right? It's the same kind of stuff when you go to the beach at Pottery Island. Those sand grains are all quartz that came down through the rivers. The most resistant stuff, because these don't dissolve very readily. Now this is really fine grained quartz, and this is really common as day on the Edwards Aquifer. It's called Chert or Flint, and it's what you make arrowheads out of. As a general rule, when you have really fine grained material, this is really super fine grained, it will be really smooth. Another example would be volcanic rock like this, that if you brought it to the ocean really quick while it's molten, it will cool really quickly and form obsidian, which is also really smooth rock. So when you see smooth material like this, a lot of times that's because this is very, very fine grained. Chert? C-H-E-R-T. I don't have it spelled here. C-H-E-R-T. Commonly it's called Flint. I'll put this here, you can check it out. So those are some of the two common minerals in the Austin area. A couple others we have are these. Pyrite. Not pirate, pyrite. Fool's gold, right? And this is what the crystal looks like in its original form. It looks like cubes. And this is what it looks like when it's smaller cubes. It's called fool's gold, right? So the way you can tell this isn't gold is because gold doesn't have flat lines on it. and gold doesn't have lines on them called striations. So that's how you can tell pyrite from fool's gold, is that they're cubes or they have sharp, straight edges on them with little lines on them. Pyrite. And that's common in the Austin area, usually where there's not a lot of oxygen in the rock, because otherwise it will rust, right? When you get iron, it's made of iron, and you get it wet, it kind of rusts away. So usually where there's not a lot of oxygen and water to wash it away. Here's another common mineral in the Austin area, it's called pyrite. I'm sorry, gypsum. Gypsum is the material that they actually use to make plasterboard out of. And this is common in the Austin area. Plasterboard, drywall, sheetrock. There you go. Throwing those technical words at me.
You don't want that in your well.
You don't want that in your well, right? It gives the water a really poor quality taste. So if you're like in the Dripping Springs area, there's a lot of that in the rock. And where the water doesn't flow through the aquifer very readily, it's still dissolving this away and it gives a real bitter taste. It has sulfur in it. So it gives it a sulfide smell, which is like a rotten egg smell, and it will taste bitter. So if you have gypsum in your water. So Jack knows he's from Dripping Springs area, protector of Jacob's Well in Wimberley. So
Is this brimstone?
I don't think you call it brimstone, but that's a good. Brimstone is sulfur, so yeah, it does have a lot of sulfur in it. So basically, that's what I wanted to cover on the basic geology of the minerals. So the minerals, we talked about calcite. When you make it into a rock, it's called limestone rock. And this is limestone rock that's composed of calcite minerals. And what's special about calcite? Who remembers? Dissolves, right. Dissolves and forms holes in caves. And that's why we have caves in the Austin area, but you don't have them further west because that is mostly composed of sand grains in the Bastrop area, where the rock doesn't dissolve away and form caves. Okay? So one other thing I'll tell you real briefly about is that we talked about the rock types, how they got laid. You know, the water levels rose, and you had material being laid behind that were composed of shells from the organisms that could take calcite out of the water. They could take this material out of the water, incorporate it into their shells, like these shells right here. They could put calcite in their shells, and you have a whole accumulation of these, or you had waves breaking down these into bits and pieces, or you have corals that are growing up trying to keep up with the sunlight because they don't want to be left behind as the water levels are rising up. So you have, after time, you have 1,000 feet of limestone left behind. Okay, and it was originally calcite, composed in a rock, becoming limestone rock. So that's a little bit of history of the minerals, a little bit of geology there for you. Some of the neat features you can see is that, like, you had mud cracks 100 million years ago, and sometimes you're walking the trails and you can still see these. These are where the soft mud from 100 million years ago dried out 100 million years ago and left these mud cracks from that time. So let's move on now to any questions on that, on the rocks and minerals stuff? Yeah.
We will always see those kind of in the museum or along the UT. They have the wall with a lot of seashell on that. What kind of rock is that?
It's mostly limestone rock because the shells are mostly composed of calcite material, like these shells here. These are, and like what she's talking about is, like, if you go to University of Texas, a lot of their buildings, you can look at, there are just tons of shells in the limestone rock. And that's usually from a quarry in North Austin, near the Cedar Park area, where they pull most of that out. It's called the Whitestone Lintel. It's like you can only find that bed within a few miles of the quarry, and then it disappears. But that is also limestone rock at the very bottom of the Edwards Aquifer. No fossils like these. Actually, it has more like these type of fossils in them a lot. 100 million years, about 100 million years. It's all the rocks in this area that were laid about 100 million years ago.
And they're all local.
All local, yes. From North Austin, that's exactly right. Exactly right. And only found in that area of that quarry within a few miles. Then that whole bed disappears.
What's the reason for calcite dissolving preferentially? Is it the same chemical composition, calcium carbonate, as the limestone, or?
It's a good question. There's slight differences between the fossils and sometimes what's filling the fossils. You know, like a lot of times they're hollow fossils, and when the shells, the lids break, and then they get filled with mud. And for some reason, a lot of times the stuff filling the fossils a lot of times can dissolve more readily. Subtle differences in the limestone is why it is. Sometimes it's a difference between having a little bit of clay in the limestone or not, whether you're having a source area that's bringing clay and mud basically, and that mixes with limestone, and it kind of makes it less soluble when you add that clay to it. So there could be subtle differences between them, but for some reason it likes to preferentially dissolve some of the fossils away, leaving the rock behind it. Good question though. Yeah.
I was curious, are there any formations where gypsum's more prevalent? Are there any, there's no gypsum caves in this area, you have to go farther west for that, but
Yes,
are
there are. And you can go see your own. If you go behind Toys R Us, Rodeo Oaks Mall, walk down the hill, you'll see gypsum like this. And that's because it's Del Rio clay. Not a lot of oxygen in it, not a lot of flow in there. I'm gonna jump ahead now. We're gonna jump into hydrogeology in the Austin area. I get lost in the Cretaceous really easily, you know. All right, I'm gonna jump ahead here. Talk a little bit about the aquifer now. So now, ocean levels came down. This is a neat graphic that the Barton Springs district put together, showing the Austin area underground. And one of the neat things about the Austin area is that we have this whole underground frontier under our feet that very few people really know about. None of us know very much of it, really. This is supposed to be downtown Austin, Colorado River, Highway 290, and the creeks of Barton Creek, Williamson Creek, Slaughter Creek, Little Bear, and Onion Creek. Yeah, thank you, Tara. And so this is a kind of a visual showing you basically one thing is you have these creeks that are losing water, and the water's going down under the ground, about 200 feet below the ground. In most areas in the Austin area, the caves are full of water. Okay, so what this is when you see the word about entering the Edwards Aquifer, an aquifer is basically a body of rock that has holes where water can enter and fill in. This is an aquifer then, and you can see in Austin area, if you go down 200 feet, there's some caves you can actually go down 200 feet and see the water running down the cave passageways. And so that's what this is. This is the water table where the caves beyond that point are filled with water. Barton Springs would be right about here. Water coming in and flowing to Barton Springs. There are wells in here it's about 15 miles from here to Kyle, Butte area and the Blanco River, which is further down. And in that area, there's roughly about 50,000 people that rely on the aquifer from their water by directly pulling water from the aquifer. Most of us in the Austin area rely on water from the Colorado River for our water supply. But in this area, a lot of people, only source of water for them is from the wells, the well water. Okay, thank you, Tara. And what does it look like down below? Let me show you. First, you can see, and people in the 1800s pretty much knew the aquifer system. A guy named Romer, 1845, it's a few years after the Battle of the Alamo, 1836 is the Battle of the Alamo, came from Germany, and he could see these kind of phenomena. Oh, you mind holding this, Tara? In the Austin area. And they put together a pretty good idea that there was conduits and caves in the aquifer that were very important in the transport of water. And so this is Onion Creek. You can see these whirlpools. These are loud whirlpools. They're taking a tremendous amount of water, going down into caves and filling up the aquifer. So we use that term recharge. Recharge means like you're recharging a battery. In the aquifer, you're filling it up with water. So you're recharging the aquifer with water. Here's a place, William Cannon and Brody, where the whole flow of the creek sometimes goes into the sinkhole and disappears. All of Kitchen Branch of Williamson Creek disappears into the sinkhole. Not the tire, but everything else does. And this is Barber Falls, a huge sinkhole that's football stadium size in Onion Creek. Big sinkhole in Onion Creek. Now, a sinkhole is basically a skylight entrance into a cave. So if this were a big cave and you had a skylight entrance in the ceiling or sunroof in a car, that's a sinkhole. That's the skylight entrance. Some of them caused by collapse because you had caves that formed from the water table flowing through, the water from the water table flowing through, and then the ceiling eventually cuts down to it's thin enough and collapses. Sometimes it'll form by just water dissolving it away along a crack and making a large bowl. So if it looks like a bowl, it was usually formed by solution. If it looks like it's upside, like it's convex, you know, like it's underhanging, then those were usually formed by collapse. So you can kind of tell the difference of the sinkhole that way. But Hamilton's Pool was collapsed, right? That would be a collapsed one, right? That's a good thing. So one of the questions was how did Barton Creek form and Hamilton Pool form? So one time, Hamilton Pool was a place where the water would go down to the ground like this. Barton Creek was the same way on Williamson Creek. Actually, Upper Barton Creek at one time used to all go to Williamson Creek. Somewhere around the area of, you know, if you know where Tony Berger Center is, somewhere in that vicinity, there was a swallow like this. It started taking water from Williamson Creek. It started taking so much water like this that water didn't flow down Williamson Creek anymore. It went into the cave. There's a cave you can go see now it's called Airman's Cave on Barton Creek, about a mile downstream of Loop 360. And that cave goes all the way over toward under Brody Oaks Mall, Westgate Mall, under the parking lot. So it's a long cave. It's the longest cave in Travis County. That was one of the original routes where water that would go underground in Williamson Creek would come to an old Barton Springs. Okay, it doesn't carry water anymore, but at that time it would carry water. In fact, it took all the water from that branch of Williamson Creek, went underground, and it caused it to be abandoned. And what happened is you had this large cave system under what's now Barton Creek collapsed. Same thing with Hamilton Pool. You had this large cave system underneath. Eventually the roof collapsed, forming this steep-walled canyon like you have both at Hamilton Pool and Barton Creek at Urban Assault Cliff. You have this steep-walled canyon that was originally a cave system, causing Barton Creek to turn and follow that cave system, which is now a creek. Thank you, Tara. So let's look at what some of the caves look like. Whole world underground that most of us don't ever get to see. Am I holding this one up? This is Goat Cave in the Deer Lane and Brody Lane. This is is this a solution or a collapse sinkhole? What do y'all think? Is it concave or convex? Is it underhang?
Yeah.
Yeah. What do y'all think? Collapse. That's exactly right. So this was formed a long time ago, and then the ground surface cut down, and you have a piece of the roof fall out.
So that was a dome. It basically fell in towards us.
Yes. Fell down this way, right? Big debris pile of material down below. This is Goat Cave Preserve, which is a neat cave in the Edwards Aquifer. How about this side? This is Midnight Cave, which is at the Slaughter Creek Metro Park on Slaughter Lane, just west of Escarpment. And I took this picture in '94, I think. Guy standing at a pile of trash. You know, this cave used to be a 20-foot drop into the cave. We'd go on a mile to trash, and I was standing on a pile of trash when we'd go down it. And now it's 65-foot drop. A lot of volunteer effort pulling this trash out. Mark Sanders, who was with Parks and Recreation at the time, led the groups, and we pulled stuff out of trash buckets at a time. Now it looks like we've restored the cave now, so it looks like this, kind of pristine. Nice pool of water. That's the water table down there. Yeah. Thank Mark. We get the main effort on it. But part of what this shows you is this was the way we learned to deal with caves. It was commonly accepted. This guy wasn't crazy. Who did the time? He's a friend of mine. I like this guy. Everybody in the United States did this, and the scientists actually weren't much of a help in the 1980s. I told you about the turn of the century, right, where people in the 1900s, people recognized the caves were really sensitive. Well, one other story about Barton Springs is that we had trouble getting our water supply in the late 1800s. We would get water from McDonald Lake, which is now Lake Austin, and the floods would take the dam out. So you had your water supply, and then suddenly it's gone, right? So in the 1920s, people looked at the possibility about using Barton Springs for our water supply. A guy named Taylor and Bond, who were professors at the University of Texas, And they studied Barton Springs. They took samples every week of the bacteria at Barton Springs. They measured the flow every day at Barton Springs, 1917, 1918. And what they discovered, a couple things. One thing, 1917, 1918, there was no E. coli, any samples they took from Barton Springs. It was very clean, pristine, okay? 1920, almost every sample they took, they started having E. coli in the samples. What they learned from that is that one thing, nobody was living at Barton Springs, so it had to be far away. Some change had happened. Someone living far away had caused contamination of Barton Springs, and it was too sensitive a supply to use for drinking water. The second thing they noticed, the drought of 1918, is that the Barton Springs diminished to about 12 cubic feet per second, and there's kind of a lower limit. Not enough water supplied during drought to supply the whole city of Austin. Certainly not now, but even back in 1920. So this was some findings that they made that was very observant at the time about Barton Springs. Now, come along in the 1980s, when they actually were starting to really develop over the recharge area, they looked at it very different. They thought caves like this were kind of a weird anomaly. They could see Goat Cave, they knew about that one, but they didn't really know about the other ones. Why? Because ranchers would tend to fill over the caves, keep their cattle from falling in. As a practical matter, they would also use caves to get rid of trash. They would line the sinkholes with mud and concrete so they can use them for stock ponds. And when it was a time of heavy development, so people at that time had a market understanding that if you didn't have caves on your property, you could develop more on it. So it wasn't really marketable to have caves in that time. Probably still not as much. The other thing, there's people like me who go around and hide cave locations because people tend to fall in these things and get trapped, and then the public says, we had to spend $10,000 on a rescue, why don't you fill it up? Like Grapevine Cave in Wimberley, they were going to back up a cement truck up to it after kids started playing in it, and they didn't seem out of control. So this is why one thing, it's really important to be able to take people into caves to understand it better. And we're working on that by building cave preserves so people can go into where the caves are safe. You can walk around and look at them. Right there. Let me show you a little bit about that. First, let me jump over to this little visual of a cave stream. So water flowing in the ground. This is in Honey Creek Cave north of San Antonio, but we have things like this in the Austin area too. This is a cave stream, and yeah.
I had heard that where the juice bar is there on Barton Springs Road, that there used to be a cave in the back of that, and that was a tourist attraction, and they'd take people back into that cave back in the.
I've heard about that too. I haven't ever seen it. There was a commercial cave downtown Austin that was called Austin Caverns on a street called Meredith, and now it's a storm sewer. But it was an original commercial cave in Austin. Now I don't know about that one, and the rocks are a little different. That's the Buda Formation. I have seen some caves that are kind of tight in the Buda Formation, which is above the Del Rio clay, above the Edwards Aquifer. But that's interesting you mentioned that, because I have heard about that. Thank you, Pierre. So what I want to show you go into next, I'm going to go back to the education thing if I have time. I'm going to go into next a little bit about studies we've been doing since 1996 to understand the flow system of the aquifer. So one thing I started doing in 96 is doing dye trace studies. These are done all over the world. It wasn't anything I came up with. It was something done all over the world to understand karst aquifers better. So we dump a dye in a place like, say, the Wildflower Center, Wildflower Cave, and we monitor Barton Springs and wells around and see where it shows up. And so what we found is that water doesn't really move like a sandbox through there, but that it flows like a highway. If you want to go from here to North Austin, you don't just drive across the Colorado River. You go on these little roads through the park, and you get to Barton Springs Road, and you make it to Mopac. And the flow in the aquifer is a lot the same way. You have these major flow paths of flow, and water 15 miles away in Onion Creek can get to Barton Springs in only 2 to 3 days. 2 to 3 days. They used to think in the 1980s they thought 3 years. But when you actually test it, in the Wildflower Center area, which is right around here, they were thinking 3 years from here Barton Springs. So we tested in 2007. We did 4 points around there. Every single one of them took 2 to 3 days to arrive at Barton Springs. All 4 of them. One of them was just putting dye in Bear Creek. Showed up 2 to 3 days. So one thing we learned is that the amount of natural treatment in the aquifer is probably really low, because we can see quite a bit of our dye showing up at Barton Springs. It doesn't take very long to get there. So it kind of highlighted what people already knew back in the 1800s, is that it's a really sensitive aquifer system. In the 1980s, they had some studies came out that thought that contamination in the Roland Wood area from like septic tanks never reached the water table. And they weren't the best of studies, and they were dead wrong. But so contamination really does reach the aquifer pretty readily. I can do a handful of dye, gets there pretty quickly, even through the soil. Some of the studies we're doing now through the soils, it takes only 3 to 7 hours to go 100 feet, 20 feet below the ground to get to this cave drip. So it can get through really quickly, faster than you might expect. I can crawl through some of these caves down the water table in a couple hours, so I know the water can get there faster than me.
What year was that study?
2007 was the one we did around the Wildflower Center area. We're studying an accidental spill if it were to happen on South Mopac or Highway 45. And I actually have a report on it if any of y'all are interested. I have some of my cards here, and I can email you the report. We don't have it on our web yet, the city of Austin there.
So the speed of travel is an indication of the porosity?
Sensitivity of the aquifer, right? That if you, for example, the pipes in your home don't filter the water very well, because water is moving through it too fast. Now if you slowed it down, moving through a sand filter or through charcoal, then you can clean the water that way. So it's a good thing. So I only have a couple more minutes. And so the other thing I was going to mention is that I've also done some studies about the sources of water to Barton Springs. And one thing surprising that we found is that the Blanco River. In fact, right now, Barton Springs is sustaining. It's kind of keeping a fairly constant flow. It plummets, usually, and then it reaches this lower level and it kind of stays constant. And what we're finding is the Blanco River seems to be the biggest source of Barton Springs during periods like right now in the drought.
And it's a totally different watershed.
Totally different watershed, that's right. It takes about 3 months to get here. Our dyes in Blanco River take about 3 months. And that seems to be the source of Barton Springs during the drought, is the Blanco River. All the other creeks have been dry for years, and it seems to be the Blanco River that's supporting the flow to the springs. A lot of the water comes from upland areas, like places that aren't the creek channels. Probably, 40-30% of it comes from upland sinkholes and things like that are actually, per acre catchment area. Those are some of the more, you get more bang for your buck on trying to preserve those areas because actually you can get a smaller area that feeds more rainfall into the aquifer and Barton Springs.
Why does it take so much longer to get from the Blancos?
Because it's a drought. I mentioned here that it only takes 2 to 3 days to get from Onion Creek. Well, that's during regular conditions and high conditions, but during a drought, it takes 3 weeks, a month to get from the same place, Onion Creek. And that's because things slow down, the gradient is a lot lower. Some of the flow paths that are open probably dry up, and so they may have to take some circuitous ways to get there.
And the Blanco's even further south.
Yeah. 3 months is what we time it from a number of traces. Yeah.
Why is there so much water in Williamson Creek right now?
Flowing?
Yeah.
In Williamson Creek.
It doesn't look like it's flowing that much, but it's there. Is this pollution runoff? Or
I suspect it could be like leakage of tap water lines sometimes. Why is Williamson Creek flowing now in some places? And I suspect, yeah, I mean, if you're talking west of Westgate Boulevard, now if it's downstream of there, you have springs that will flow all the time. Yeah, like say McKinney Falls, those are probably spring fed. And some of those will flow during the drought of the 50s, and that's because they have old Colorado River alluvium, sometimes, or limestone rocks like the Buda and Austin Chalk. They're holding water there, and they have clays underneath that keep it from going deeper, making springs. That's probably what we're talking about there, yeah. Some creeks like Waller Creek now are flowing a lot because of probably urban leakage, like water lines, irrigation, things like that are supplying a regular flow to the creek now. Yeah.
Did you say what actually causes the water to spring out here?
So when I talked the original story about Airman's Cave coming here at one time, basically what you have is a cave that intersects the creek, and it's acting as a drain for the aquifer. and coming out at certain points. That's why water just doesn't pour all along Barton Creek, but it comes out of a certain cave under the pool and a certain conduit probably in Eliza Springs and an Old Mill Spring. And that's because you have a cave that's coming out at the surface there and draining out the aquifer.
The elevation of the Blanco River must be higher than the elevation of Barton Springs, and it's hydrostatic pressure that forces the water out here.
Right, and if you look at USGS website for Blanco River, if you look what the flow was about 3 months ago, that's a lot of times what Barton Springs is flowing at now during the drought. Yeah.
Can you show us the Williamson Creek, Barton Creek capture deal? I'd heard that
How about this?
a long time ago, I guess it was Steve Stecker or somebody was talking about how maybe Barton used to be, or Barton, the main part of Barton used to be Williamson, and then it got...
So this used to come to this. And you had a whirlpool forming somewhere around here at one time, causing the water to go all underground, abandoning this route here, causing this to be the cave system. And Airman's Cave basically goes from here to here now. This becoming a steep wall canyon, because that was an old cave system.
So Barton Creek used to look like West Baldwin and East Baldwin.
Yeah.
Stubby.
Yeah. We pirated Williamson Creek. Hi. One last thing I was going to show y'all before, if I got one more minute, right?
Yeah. You gotta cut it off quick.
All right, quick.
We got another speaker coming up.
I know, I'm sorry. All right. Well, I did want to tell y'all that, as Bruce said, we are working on getting y'all on the aquifer and in caves. Best way to understand it better. And so we have some karst preserves. You can go right now on Deer Lane, Davis Lane. If you go Davis Lane, 1 block west of Mopac is the Village of Western Oaks Karst Preserve. Another one is on the east side there between Brody and Mopac. You can walk through right now, but we're currently in the process of trying to dig caves at the Wildflower Center, some of the high schools where the kids really would like to get into caves, and we want them to do it safely. We're also working on the Go Cave Karst Preserve to make more caves we can take people into. We have a shortage of it now, believe it or not. Any other questions? I think I got to stop.
You were going to speculate about the age of the springs itself. What do you?
Yeah, I told you about their origin, but they have some estimates on the age, but I don't know what those are. That's a good question. There was an old original Barton Springs.
What percent is the aquifer actually full right now?
It's pretty low.
In terms of total
total water in the aquifer. It's sort of like your bathtub where you have about 3/4 of it full of water, but a lot of it down below isn't really moving, and you have that upper drain that kind of overflows. It's a lot like that. So probably 2/3 of it has water, but a lot of the lower 2/3, the water doesn't really move as much. It's one way of looking at it. Okay, thank you all very much.